Okay, so we're going to talk about the applications of conservation of energy, all right? So conservation of energy. Okay, and we learned before that energy E is never created or destroyed, only converted to other forms. So we've covered that, and we've also talked about some various different concepts in terms of energy, right? So we started it all off with work energy theorem, that working is applying a force over a distance, and that if you do it in the right way, this can store potential energy. Okay, and we learned that when you have stored energy, that stored energy can be used to do work. Okay, and so some examples of potential energy that we talked about were gravitational potential, which worked out to be mg times h. And that applies to this because if you were to lift something up, right, the force applied here, the lifting force, right, would have to be equal and opposite to mg times whatever height you went to. You'd have to put that amount of work in, and then once this is up high, it can do work for you as it moves back down. Okay. We also derived kinetic energy. EK is 1/2 mv squared. An object with a velocity and a mass can do work for you, right? You can, if you have a big heavy brick, it can smash into a nail or maybe a hammer or whatever, and it can apply a force over a distance to like drive the nail into, say, the wall. And you can also have elastic potential energy. So if you do work to, say, stretch a string or a elastic or something like that, that elastic will store that energy and it can be released. So there are ways to convert these forms of energy back and forth into each other. Okay, and that's what we're going to kind of look at. Now, a couple of things. We're going to ignore the second law of thermodynamics, which says that in energy formations or transformations, some energy will always be like lost as an unusable form. It's not like it disappears from the universe. It's just that it usually as heat bleeds off into into the atoms in the atmosphere around you, right? So we're going to ignore that. We're just going to say that energy is always conserved. So in a system, whatever the starting energy is, will be the same as the ending energy. And just if we want a picture here, right? If we have a spring and we compress the spring, right? We have to apply some work times the distance. This is just a variable amount of force that you have to apply, but due to Hooke's law, right, we worked out this formula, and as long as you know this K value, which is the spring constant, you can figure out how much energy is trapped by how much work you did to begin with to push it in there. So let's just, before we do any numbers here, let's just think of a couple of scenarios that we could have. Like, just make some things up. So let's say we have a ball, and we put that ball at the top of a track. Okay. So here it is. Here's a track. Track has a ramp, and the ramp has a spring at the end of it. So you had something like this. Okay, here's our system. This has a mass. Okay, this is our system. Okay, let's say right at the beginning, this has 0 velocity. Okay, so let's talk about the total energy of this system. Well, the total energy right now with nothing moving is all in the form of gravitational potential energy, right? The ball is up high. It has the potential to do something, right? Now let's say we like shuffle it over to the edge, okay? So we take this ball, and we move it right to the edge of the ramp, and then we let it go. Oops. Here. There it is. Okay. So have we have we changed the overall energy of the system at this point? The overall total energy of the system, right? So just think of conservation of energy, right? It says that E is not created or destroyed. Right. Correct. Exactly right. So what we're going to say is we're going to say that the E total of the system is we're going to make up a number. We're just going to say it's 1. It's 1. Okay? Are you with me? It's 1. So what that must mean then is that at the beginning, gravitational potential energy must be equal to 1. Are you with me? But now look what's happening, okay? This thing is losing gravitational potential energy. It's going away, right? It's going away because it's getting lower towards the bottom or ground state or ground position here. So EG is decreasing as we go, but we're not able to lose any energy. So it must be getting converted into another form, and it is. It's turning into EK. So at this point, the total energy of the system is equal to 2 things. Whatever EG we have left, so we'll call that EG prime, plus whatever EK, kinetic energy, it's gained by that losing that, right? The total energy is still 1 though, right? It's still 1 for the system. It's just now spread between 2 things. Is this making sense so far? Okay, so let's take this thing and let's move it forward again. So now it gets down to the bottom. At this point, does it have any gravitational potential energy at all? Ooh, sorry about that. Right, it has no height. And I should put that this is EG2, right? Because there's some EG left. Right, so EG has now dropped to nothing. There's no more gravitational potential energy at all. It's all in the form of EK now, right? And now it's zipping along at the highest velocity it will ever possibly have. Okay? Are you with me? Then it's going to collide with this spring, right? And it's going to push the spring to the right. So as it collides with the spring, just grab it here, move it over here. It is going to compress the spring down to some maximum compression. And let's say this is the full compression of the spring, right? Not that we run out of spring, but that just this is as far as it goes. At this point, there is 0 kinetic energy, right? Because the ball has stopped moving. But what we have done is we have turned all of the total energy of the system, right, at this point is now in terms of spring potential energy. And that is now 1. Okay? At this point, the total potential energy of the system was in the form of EK, and that was 1. Now what about when the spring is partially compressed? What happens then? When the spring is only partially compressed? Right. E total, in that case, because the ball will still be moving, but the spring will be partially, compressed. The ball will be moving slower because some of its velocity got eaten up by compressing the spring. So then we've got some in the terms of EK, so we'll call this like EK2 prime plus some spring potential energy. And I think I was calling it EE before, but now I'm calling it ES. Just don't get confused. It's a spring, so I'm calling it a spring, but EE and ES is the same thing. So for this entire scenario, right? This entire scenario, the total energy has always been 1. It's just converted forms, right? Now what would happen after this? Once it's fully compressed the spring, what's next? Right. Yeah, it would spring back the other way, right? You would flip the direction of velocity, but all it would be an EK here. Then it would rise up this, slowing down as it did so, until it got to the very top, where it would stop. And then it would roll back down, and this would continue forever, right? Why does that not happen in real life? Because friction, energy losses heat in the real world, right? Sound, yeah, exactly, right? Springs get hotter when you spring them. Try it sometime. Yeah, so there you go. This is kind of like a scenario. Now, all we're going to do is put numbers on this, right? We know formulas for all of these, so we can write them in there. And if we know the total energy, we can figure out all the information we need, right? Based on a drawing like this and our understanding that in a system, the total energy is always the same. So here's an example from some work that we had. It says, what upward velocity must an athlete have in order to clear a 2-meter high bar? So this is a high jump question, right? So I'm going to try to draw a high jump, see if I can do it. So here's an interesting thing, right? High jumpers like flip over backwards. The bar like comes under their bods, right? Like this. Yeah, perfect. Great drawing. Okay, so there we go. So he's flipping over backwards. And now this is a little bit misleading, right? The reason it's misleading, or not misleading, but there's a little more physics here than meets the eye, okay? This is 2 meters high. This guy has to get like part of his body over 2 meters high, but by jumping in this way, his center of gravity actually would pass under the bar. I know we didn't really talk about center of gravity, but by doing this back flip, back arch over the bar, you actually can expend less energy than if you say like got your whole body up over it, like you tried to like jump right over, because then this center of gravity would have to pass over the bar. So this actually increases the height that you can go over by decreasing how high your center of gravity has to go, okay? But anyway, oh, and it also tells you this. It says the center of mass is at 0.85 meters before the jump. That's kind of important, right? So what's the center of mass? So what that is it's the point on your body that is essentially where it's as if all your mass is concentrated, okay? It's like, it's hard to explain. Like on a sphere, on a perfect sphere, the center of mass would be like right in the center of a sphere, right? Okay, so it's like with the Earth, and you're talking about gravity and the center of gravity, it's as if there's a point in space at the center of the Earth, because it's nearly a perfect sphere, where the Earth acts as if all of its mass is concentrated. On a human, that's like right around your belly button, okay? So if you think about the fact that your legs are pretty heavy, you know, your head's pretty heavy and so on, but your arms are kind of light, it puts your center of gravity a little lower than, say, maybe in the geographic center of your body. If you had like an oddball shape, right, you would have to like average out all the mass, and you have to find, okay, this is more mass, this is less, and it would put the center of gravity somewhere weird in it, okay? So you have to get your center of mass over the bar. So from 0.85 meters up to 2 meters. So what you have to do here is you have to essentially give yourself some EK, and you have to spring upward and turn that EK into EG, okay? And the height you have to get is going to be equal to 2 meters minus 0.85 meters. So I guess the assumption here is that you're actually having to get your center of mass over 2 meters high, is how we'll have to interpret this, right? So what do we have then? Well, you'll notice that no mass is actually given. So 1/2 mv squared is equal to mgh. Mass goes away. So what that tells you is this. How high you jump is strictly dependent on what velocity you have when you leave the ground. So if you like want to learn about how to jump higher, is by making your velocity higher when you leave the ground. There's probably a lot of ways you can do that as a person, right? But there's lots of big heavy dudes out there who can jump really high, but it's probably because they have super powerful legs and they can get a really high velocity. So it's not just that, it's not as simple as like, heavy people can't jump. You see football players that go up and dunk the football on the goalposts all the time. That's 10 feet high. They can dunk a basketball and they weigh like 300 pounds, right? They just have super powerful legs. They can get that velocity up there. If you're like me, you can't really jump because you're not powerful enough to drive your body off the ground to get a high enough velocity, okay? So you can get enough velocity, right? Mass doesn't really matter. One way to get more velocity, of course, is to keep strong legs but lose extra mass, okay? So let's figure this out. So if you look, what we're solving for here is V, and then V will be equal to 2gh, which we've used before in kinematics, and I pointed that out the other day. So 2 times g times 2 minus 0.85 meters. And what we will get at the end of doing the math is 4.7 meters per second is what we get. And there you go. Okay, so let's try another one. A bullet is in a ballistics test. Okay, so in other words, what we're doing here is we're trying to figure out how the properties of a bullet in flight, which you can't really measure directly unless you have, I guess, like pretty specialized equipment. Maybe you can do that nowadays, but in the old days, you couldn't do that. So what you would do is you would take a bullet, and so we'd say to find velocity, the bullet is shot into a sandbag. Okay, into a sandbag. So I'm going to draw a picture because a picture is worth at least 50 or 60 words. And so here's step one. Okay, on the bottom of here, we're going to put a sandbag. In the right spot. There's my sandbag. Okay. Oh my goodness. Why does it automatically assume I want to change the background color? Okay. And here comes our bullet. Right? Zipping along, probably at a super high velocity. We want to know what that is. And the bullet's going to stick in the sandbag. And that is going to cause the sandbag to rise up, right? To swing back on its rope here. So it's on a rope. Uh-oh. Uh-oh. No angle. Because I guess we could put an angle if you really wanted. But what I'm kind of getting at here is what we're going to look at is how high does the sandbag rise, right? So here's the bottom of the sandbag to start. Here's the bottom of the, oh, come on. Okay, so what we have here, right, is we have a height, right? We would know in our testing facility the mass of the sandbag. We could weigh the bullet, right, after or before or whatever, right? So this is m, or if you want, at the start of this part, m plus m. This is the height it rises to. So what we can figure out is how much energy was there when the sandbag started to swing, right? So we could say then, Eg equals m plus m, that's mass of sandbag plus mass of bullet, times g, times the change in height, or delta h, okay, times the change in height from lowest to highest. That will tell us how much energy there was at the beginning, right? And we could say all of this energy must have been in the form of Ek right at the start, right? So this bullet comes flying in here, and it gives the sandbag bullet combo an Ek, which then swings up to some height. So let's put some numbers in here. It says that the mass of the bullet is 20 grams. It says the mass of the sandbag, big M, is 10 kgs. And it tells you that it rises 0.040 meters. Okay? So step one, find Ek of bag/bullet. Okay, so the bag bullet. So we're going to do that by saying, well, whatever it had in EG must have come from the EK it had just after the bullet smacked into it. Okay, I'm going to make a little notice to you here, though. Why can't I go directly from the EG here to the EK of the bullet? Does anyone know why? What kind of collision is this back from when we did momentum? This is an inelastic collision. And energy is not conserved in inelastic collisions. Don't ask me why. I don't want to talk about it. So yeah, little dark secret, in an inelastic collision, we do not conserve kinetic energy. If you try to do that, you'll get a crazy answer. It won't work. We'll deal with this later, but we'll use our old friend momentum, because he always works. Okay? So step one, let's do this. M plus M times G times H equals 1/2 M plus M V squared. Well, our M's don't really matter. Get rid of that. Okay, what we want to know then is, what was the velocity of the system just before the crash? So we get that. Sorry, what was the velocity? Sorry, I said that wrong. I trailed off and I didn't say the right thing. The velocity of the sandbag bullet system just at the very beginning, before it's had a chance to slow down or rise up at all. Well, V equals 2 G, and our height is 0.040. V equals what? Okay, so we get an answer of 0.9 meters per second. Okay, that does not tell us anything about the bullet. But we just learned we can't use kinetic energy anyway for this, so we're stuck going back to momentum. So what happens here? In a momentum scenario, we remember this, mv plus big MV equals mv prime plus big MV prime. If this is the sandbag, does it have a velocity at the beginning? No. All the momentum in this whole scenario is in the bullet. Why do we have to use momentum again? Right, because EK is not conserved, okay? And then over here, both masses are together, right, after. So we get the MV of the bullet equal to M plus M times the new velocity, which we just found using energy. And now this is solvable. Now using momentum, we can find out what the bullet velocity is. So V equals M plus M times V all over little m, and our numbers. 10 kg plus, what was the bullet mass? 20 grams? So 0.02 times the velocity, 0.9 meters per second, all divided by the mass of the bullet, 0.02 kg, and I think you'll get a nice big number, which is, anybody got it for me? 450 meters per second? Perfect. If you did this with kinetic energy and assumed that kinetic energy was conserved in this collision, you would get a very low number and you would not get an answer that worked or made any kind of sense. Okay, I'm going to leave it there for today because we're almost out of time.